Hello everyone. In this video, we are going to take a look at Chapter 7, Section 17.4. Previous video or previous section, we're looking at things that are not rotating. In this one, we are going to look at the bodies that are rotating. So starting with the definition, when a rigid body rotates above a fixed axis perpendicular to the plane of the body at point O, the body's, let's say, center of gravity is at G, moves in a circular path of radius RG. So the acceleration of the point G can be represented by the tangent component and the normal component. Tangent component AGT equals RG alpha, and the normal component AGN equals RG omega squared. Since the body experiences an angular acceleration, its inertia creates a moment of magnitude, Ig alpha, equals to the moment of external forces about point G. So the scalar equations of motion can be stated as these three belows, and then so Fn on the normal direction, you have Agn, which will be mRg omega squared, and then on the tangent component, Ft equals Magt, where that will be mRg alpha, and then the mg, the moment about g, will be Ig alpha. What over here is that if we are going to look at it about point O, so they derive the equations for us. We can write the three equations of motion. If it's about point O, you have Fn, same thing. Fn equals mgn, which is mRg omega square. This is the same as if it's about point G. And then Ft will be Magt, which equals mRg alpha. But about point O, you have IO alpha. About point G, you have Ig alpha. Now, general steps when you're solving problems like this, you're going to establish the n direction and the t direction, normal and tangent. We're going to draw a free body diagram showing the resultant inertia forces and couple. We're going to compute the mass moment of inertia, Ig or Io, write three equations of motion, and identify the unknowns, solve for the unknowns, and then use the kinematics if there are more than three unknowns, since the equation of motion only can solve three unknowns. Let's take a look at some examples. This thing, yes, definitely rotating. And in your statics class, you learn that point O is going to be a pin support. So that means you have constrained reaction force coming out from two directions. That's a pin support. So we know the mass of the rod, we know the radius, velocity, angular velocity, angular velocity 5 radius per second. And then we have the moment, which is 16 Newton meter applied to the rod. We're looking for the angular acceleration alpha and the reaction at point O when the rod is in the horizontal position. So at that moment, we know that pin support, so you have two directions of the reaction, support reaction. You have ON and OT. Moment is going 60 Newton meter going clockwise. And then you have the weight coming down. And then the kinetic diagram shows you have MAT and AN, two different directions, plus IG alpha. Okay, so we're going to put that in the equations on the left. MAN equals MRG omega squared, and then MAT equals MRG alpha. So plug that in with our ON and OT. That will help us solve. Oh, wait a minute. The third equation, sorry. You have sigma moment zero about point O equals IG alpha plus MRG and then alpha R. Since it's a rod, we plug in the formula for Ig, mass moment of inertia, for a rod will be 1 over 12 ml squared, and then Rg is going to be half the length of the total rod. And plot all those in, we can solve our two unknowns, alpha and OT. ON, we could solve that as well, but since the problem is asking for angular acceleration and the reaction at pin O. So yes, so we are solving the alpha OT and ON is out there as well if needed. Next thing is ON right here, 750 Newton from our first equation. That's only one unknown there. Okay. So next problem, this thing, when the rope is being cut off, it's definitely going to rotate. So we're gonna we're gonna draw our free body diagram, knowing the mass is 15 kilogram. We know we're looking for the reaction at the pin O. So again, pin support, you know that reaction support coming out from two different directions, and we're gonna do it ON and OT on the tangent component and the normal component. Looking for the reaction at the pin O and the angular acceleration of the rod just after the rod is being cut. So you have in your free body diagram, you have mg, the weight, and then O and OT support reaction from the pin support. And then on the IG, since it's rotating, right, kinetic diagram, you're going to show the rotation, and then you have your MAGN, MAGT, so two of them. So we're putting that together. Notice that your ON equals 0 Newton horizontally, since horizontally ON is the only force. Okay, that means that force got to be a 0, so that it can be an equilibrium. That's why mRg omega squared equal to 0. And then the rest of them, again, we're looking at a rod, plug in the IG, that will be 1 over 12 ml squared. And then your RG is 0.15. RG is the distance from center of gravity, which is the middle of the rod, to the pin support at O. That's where that 0.15 come from. If you don't see it, this portion from here to here, okay, and then total distance is 0.6, and then this distance, that's the arrow pointing to, is 0.15. Okay. Next thing is that we plug in the value of IG and the RG 0.15, and then do mathematically. I'm not going to go over the math with you, but from three equations we're solving for our unknowns. We can look for the O tangent. Since O normal equal to 0, O tangent we have a value for O normal, and we also reaction and looking for the angular acceleration, so which is alpha, right? We plug in here to get the value of alpha. Next problem. So over here we have weight, spring support on the right end, pin support on the left, 100 Newton in the middle. The weight of the rod we know, and it's horizontal. And then we're looking for the angular velocity of the rod and the acceleration of the rod mass center at the instant the 100 Newton force is applied. So at that instant 100 Newton supply, reaction force from A, you both have AT and AN, and then reaction force of B, you only have the vertical. Okay, and then since it's rotating, we have IG alpha and then a MA tangent and MA normal. Okay, so we're writing our equation, and then one thing is that right before the 100 Newton, the spring is supporting half of the rod's weight. Why is it half of it? Because it's on one end of it. Because if you do a summation the moment about point A, right, since the spring support is 2 times, you have a bigger moment arm, 2 times support, 2 times the moment arm, then the moment arm of the weight. That's why it's supporting half of the rod's weight. Okay, and then keep going. Equation of motion says sigma ma equals ig alpha plus mrg alpha r rg, and then you plug in our values. And again, it's a rod. We know the equation to calculate the ig for the rod, and then your rg is 1.5. And then substituting, we can calculate the value of an and at. Okay, keep going. Our last group problem. The moment this thing is being cut, you have a 30-pound sphere and a 10-pound rod. We're looking for the reaction at pin O. Again, it's a pin support. You have your OT and your ON. Okay, so we draw our free body diagram, OX, OY. And then over here you got 10 pound on the rod, 30 pound on the sphere. And then your kinetic diagram, since we're rotating, don't forget you, in addition to your MAT, MAN for both of them, you also have the IG for the sphere, and then IG sphere alpha, and the IG rod for the alpha. So putting them together, since OX is the only horizontal component, that's why you're having a zero. Okay, and then we're writing our equation, putting all of the vertical forces together, and then over here you have all of the vertical mass times velocity, and then get a relationship between a y and the alpha. And then the moment equation, you have 30 times 3.0, 10 times 1.1, right? Because you're doing it about the center of gravity and doing the moment about point zero. And then the right hand side will just be the IG alpha, and you have two of them. One is for the rod, one is for the sphere. Two equations and two unknowns. We're solving for the value of alpha and y. Okay, that's all I want to share with you in this video. Hope you find it helpful, and thank you for watching.